Welcome everyone to another installment of the Nano Educators Quarterly Forum. I just realized today that this is the third anniversary of the forum. Our first meeting was 3 years ago in April. This was hosted by Marielle Kolker, who's one of our co-hosts, who could not be here today. But I'm really excited for the network that we built and that we keep building. For everyone new, my name is Maria Fernanda Campa. I'm a staff scientist at the National Technology Coordination Office, and we facilitate these forums with Daniela Duran at Nano at Stanford, Mariel Coker, a physics teacher in New Jersey, and all of you, because this is really driven by the teachers that connect every quarter and shared by your interest. Today, let me, s- we have an exciting forum. We will be discussing nanotechnology and NGSS aligned lesson plans developed and piloted by teachers. And today is a very special session for me. Sorry, anyone? Okay. This session will highlight free nanotechnology lesson plans developed and piloted by middle school and high school teachers, inspired by Nano for Earth activities. For new people here, maybe you have not heard about Nano for Earth. Nano for Earth is a federal activity that I have the privilege of leading that brings together the nanotechnology community from different sectors and stakeholders to really drive the acceleration of innovative solutions to protect the earth and its environment. Thanks to the work of the incredible group of teachers, include our speakers today, Marianne and Merrick, and led by Eclipse and Jen Cow here in the call. The summaries of various public meetings organized by the NNI were translated into accessible lesson plans to share and inspire students. Um, I find government documents very inspiring, but I'm pretty sure the students would just go to bed if they were asked to read that. So, if you want to learn more about Nano for Earth, please go into nano.gov. And without further ado, let me introduce our speakers for today. Marianne O'Brien from Lincoln Middle School in California and Merrick Chang from Los Altos High School in California will do a deep dive into two of the lesson plans that they develop as part of this activity. The lessons plans will focus on nanocatalysts and friction reducing interfaces and all the wonderful nano things related to that. And with that, I'm going to give the floor to them.
Thank you so much, Maria, and thank you everyone who's joined us this evening. I'm Mariana O'Brien, and I teach eighth grade science at Lincoln Middle School in Santa Monica, California. It's a public school. Some people, when they hear Santa Monica, they think, I'm a classroom teacher. I want to share with you the lesson that I designed with several other teachers, Lynn Ho, Huerta, Mariel, Kelly, McKeon, and also Merrick. And without the help of Jen Chow, we couldn't have done this. So thank you so much for being there. I'm going to share my screen right now, and I'm going to go over the layout of how I did my lesson. And it's going to be the same format uh, for when Merrick gives his lesson as well. So hopefully that'll be useful for you. I'm also going to then dive into a couple portions of the lesson that I think might be a little bit tricky. And I want to primarily focus on showing middle school teachers how to get the nanoscience into their classroom. Because sometimes trying to fit this exciting topic can be a challenge. And I think I found a way that will be useful for many people. So if you're here on the site, you'll scroll down, there's the high school, but we're going to do the middle school one right here. And it's about friction, energy, and energy efficiency. So when you click on it, you will see initially the standards. This is like a typical setup for a lesson. The lesson overview, the materials that you'll need, and then it'll dive right into day one. Before I continue though, Merrick, I forgot to mention, like, what do you all hope to get out of our conversation? Do you mind dropping that in the chat so I can make sure to include that if I can fit it in? Like, what do you hope to get from today, from Merrick and I in these lessons? Thanks, Merrick. Do you hope to get ideas? Do you hope to get resources? I'll let you think of that and I'll keep going. So, hi. So here are on each day, there'll be some objectives and then nano core concepts, and then ideas about the essential principles for climate literacy. We broke down, oh, great, perfect. Thanks. Okay, that helps me. Thank you so much. So I'll be sure to focus on where we have extra resources for you to take the lesson where it might best fit in your classroom. The lesson's been broken down into three parts: the opening, the body, and the closing. You can think of the opening as you like, as the explore, if you do the 5E model or whichever model you use for your lesson design. But we try to keep it really simple so you could manipulate it in a way that is helpful for you. Oh, exciting. Look at this. Expand robotics. Nice. We have got to talk. Okay. So we put some questions here, what the teacher will be doing and why it's important, and then what the students are doing and how does it connect to the phenomenon, and then a picture for understanding. So this lesson has 4 days, and I'm going to scroll back up here. And what I try to do here is make it really compact. And for my students, when we started doing this, we returned from the pandemic. Many of them didn't have the skills that we expect from other students to be writing and taking notes. Understandably, they weren't, in our classroom for a while. And so I developed this system where I have just kids take a note, a piece of paper, and fold it into 4 squares. And that way, I didn't have to copy a handout. And we had each of the squares mean a particular thing or an activity or thinking task. And I'll show you what I mean by when we go over that. Here are the slides, and this is the same slide deck for all 4 days. I put here what slides are for the particular day. Down here are some optional materials. We also put down here materials you'll need for day 3, because there are some materials like a cabbage leaf or a kale leaf that you can pick up. And we try to make them not very uh, readily available, is what we want them to be for you. So are there any questions about this setup so far? Looks like pretty traditional. Okay, great. Now I'm going to dive right in, because for day 1, how my year normally starts is with energy. And we talk about all the different kinds of energy, the transfer and the transformation of energy. And I wanted to find a way to fit in nanoscience. And I didn't want to have a whole separate unit on nanoscience. I wanted students to see how it's incorporated throughout the year. And so when we talked about energy, it's a natural question that most of you probably ask your students is, well, where do you get the energy to ride your bike or your scooter or play baseball or swim or whatever activity you do? And I was focusing on the scooter because this was at the beginning of school, and I just noticed there were so many scooters around. And you have to clarify, for this particular activity I did, it's not an e-scooter. It's a scooter that you have to kick with. And when you ask students where do you get that energy, then they have to realize, oh, it's from themselves. And so that would be like the opening phenomenon that we used. And I'm going to show you just day 1. Let's see here. Okay. Let me put this over here. Oops. Can you still see my slides? Are you good? Yeah. Okay. I'm gonna present them, like slideshow them. Okay. So this is the title one, day 1. This is what I was mentioning about how I have them make this 4 table, and this is literally the slides that I use for my classroom. So if you want to delete these when you get them to make just do whatever you like for them. So they take a piece of paper and they cut it into these, like they fold it into these 4 sections. Here is the phenomenon I was talking about. What are some ways that you get around and introduce this to your class however you normally would? I was using a scooter. And the key question that really turns it into nanoscience is have them think about what happens, what would have to happen to make you go farther with just one push of your when you kick on your scooter. Um, okay. And then we talk about like why would it take what would you have to do differently to go farther than you normally did? And they intuitively understand this idea of friction. And so they love this video of the rock. I don't know, they just love it. And so they're all doing this when they see it. I thought was really surprised how much they would like it. I hope you don't mind me going through this in detail so that you don't have to spend time doing that when you dive into the lessons. You can just go right to day 2 to see if this might be something that fits. Have students write some notes down, and then for understanding here. So what would have to happen to either what you do or the surface or your transportation, whichever one you're using, a bike or a scooter here for this example, for you to be able to go around a soccer field with just one kick? What would it take? And that gets them to talk about all different sorts of things, and invariably friction comes up. And hopefully, this is where you can either continue down this path with friction and then go into your forces, if that's the next for us, that would be the 3rd unit, or you could talk more about energy. It's really up to you. This is like a fork in the road for you to decide how this works. But for me, I just continued on with energy. Talk about nanoscience. You need to have students understand the scale of things. And here I put some detail about the difference between a million, a billion, and a trillion. Maybe you have your own activities that are really effective. You can do that. Or you want something different. You can do this one's really pretty simple because we talk about $1 trillion. For my students, a million is the same as a billion, as the same as a trillion. So helping them to understand that is significant. In addition, most kids don't know what GDP is. They're like, who cares? What is that? And so I have to explain to them about the economy and this whole idea of we actually lose money based on the thing that we're talking about. And not just a little bit of money, a lot of money. And so I have them take a few notes about this. We focus on what a trillion is. And we talk about if you're going to just count to a million, how long will that take? If it was just one number per second, it's about that long. How about a billion? I have them like, I show them because I want the expanded version. I also want the scientific notation because many of them are doing it. And then I have them guess, what do you think? And they think, 31 years. Oh my gosh, that's older than you, Miss O'Brien. Oh, thank you so much. That's so nice of you to say. But, then I say, well, what is a trillion? And for kids who understand the exponents, they seem to get it instinctively. But in my classrooms, it's not like an honors or it's just a regular science. And all students are in it. Students who have 7-8 math or in 8th grade, or those who have geometry. But when they realize that it's so much longer, they go, there's a question. I can't see the question. I actually clicked my hand for the question. Oh my gosh, I think I clicked my hand for the question. Sorry, let me.
Oh yeah, it's you. It's no problem.
It's been a while since I've been on Zoom. Sorry. Okay. So you can use this as you like, or when you make a copy of the slides, delete it. But please feel free to do it however you like. But once you've made your paper with the 4 boxes in it, then and you had your students number and letter it, I have them do different tasks. So the first task, this one is to write these calculations down. So they remind, it's like thousands. It's not just 100 or double, it's like thousands. And I found it super helpful for students to do that. You could also even do like paper If you have them measure a ream of paper is 500 sheets of paper, you could actually measure 2 reams, that's 1,000, and then have them make a scale on your wall. I've used just like tape for a meter to get the idea of a million, a billion, and a trillion then as well. And then GDP, like this is they don't really know what this means, but I just kind of tell them this is what it is, and then I move on. That's all the time I spend on that. But there are stations, and for the first set of stations, we do station A together. And station A talks about, this is a square paper, talks about sports. And when I ask students to think of their favorite sport, I invariably say, where's the friction? And they said, well, mine doesn't have friction. And they actually all have to have some friction. But then we talk about the equipment. Does your equipment increase the friction or does it decrease? And exactly where is that happening? If you want to intro this with curling, some students didn't know about curling. Most kids did, but some didn't. And there's a little video in the lesson plan about an optional video about curling. And I think it's NBC makes the science of sports, and it's one of those. So you do station A with your class. These other stations right here are not lettered because on day 2, your students get to choose 3 of the 4 stations. This paper right here it's not a lot of space, and it's that way on purpose. The slides for these stations require them to do something and then a discussion. It's the conversation with one another that's going to help develop the thinking. This is just for you. You're doing this slide with your students. These are the 4 that they would choose from. And so you can see, it's not light blue like it'd be a hyperlink, but they're underlined. These are the actual hyperlinks that you would use. So here's an example of one that you do with your students to give them an idea about look, you sit with their partner, and if you want, like during this time, I have usually assigned seats, but then I let students like choose, sit with someone you want to work with today for this first station. And here's some examples. Tell them to only take up half a square. And they're going to rank these from least friction. And you can talk about why you say that. Here's the second one. And this one, which things decrease the friction in the particular sport? It was really interesting because some students taught me about like gymnastics and surfing. Because I haven't done gymnastics in years, and surfing I've not, can barely stand on the boards. That doesn't really count. So I learned a lot from them. I'm going to continue here. You are going to have them flip over because the A, B, and C are on one side of that 4-folded paper, just 4-folded paper. And on the back are the 1, 2s, and 3s. And you have some notes here. These are all hyperlinks here. They're the correct, coloring for you to be able to see that. Oops. Day 2 will start. And we again talk about this idea of how friction produces wear. It also produces heat. And that heat is kinetic energy that's not being transferred as kinetic energy. It's being transformed in another form of energy. Before I continue, are there any questions? Okay, I'm going to go back to this one. Am I back to the lesson plan? Oh, there we go. Wait, am I back to the lesson plan now? Yeah?
Yes, you're back
Okay,
to
perfect.
your browser.
Great. So here is another optional lesson in day 1 about uh, comparing million, billion, and trillion. You can go to that in detail if you like. Here, I put down the text because some of the links to this tribology article wouldn't work for my students. And so I had to, take the copy of the text and put it in a document that they could use. So maybe it will be fine for yours, but just in case it's there, and there's the answers. And here's the link to the Science of Winter Olympics about curling. That's a really fun one that they like to do. Here's some extended ideas, but it's the same format for day 2, day 3, and then day 4. Day 4 is a project where they come up with an idea that reduces friction, which in addition reduces heat, and or I have them work on something that addresses climate change using biomimicry. It's up to them, because day 3 has a portion of the lesson about biomimicry. How can we use nature to help us engineer products that either reduce friction or reduce heat or reduce both? I think, unless there's no questions, I'm going to let you take it away, Merrick. Am I missing something? Is there
No,
something
you
that
know, you that was awesome. Yeah, that was perfect. Thank you, Mariana. So just I just want to preface, again, my name is Merrick. I teach high school science out in Hacienda Heights, La Puente area, Hacienda La Puente Unified School District, about 20 miles east of LA. I'm gonna be honest, like I am a teacher I'm like a civics teacher masquerading as a science teacher. So I'm just be very honest. Like, so when I came to this group and kind of, I'm gonna be learning from you all and kind of sharing a lesson that some of the other teachers kind of developed and I got to kind of work with as well that I got to try out in my class. One of them was Mariana's lesson. So that friction lesson, I know it was, she talked about middle school, but it was a big hit with my freshman students as well. So with that being said, we're just going to dive into another lesson that talks about catalysts. So another aspect of how you can introduce nanoscience into your classroom. For myself, this was through the lens of human activity and climate change. So that was just the avenue I went specifically with this for this lesson. But there's different avenues, and this is just what one aspect might look like. So I'm going to share my screen and then I'm going to jump right in. Sorry, y'all going to see yourselves for just a bit, but y'all good? Awesome. Okay, so again, just to kind of go off of what uh, Dr. Jen Cow had thrown in the chat. This is a nanoscience toolkit on Eclipse. And if you look here, there's actually a total of 4 different lessons that you can kind of look through that span from coatings of lubricants that Mariana just talked about, also battery and energy storage, greenhouse gas capture, storage use, and catalysts. So for myself as a high school teacher, I'm going to look at the unpacking plastics, and these are both scaled for high school and middle school, so you can kind of access it from different points. So if I click here, it's going to take me straight into that Google Drive that houses the lesson. And just as Marianne talked about, I wanted to give a brief overview, kind of like my perspective is going to be from like the 10,000 foot viewpoint looking in. So from the top down, every lesson comes with a time estimate as well as the NGSS standards that are aligned. Every lesson comes with a specific lesson overview, so learning objectives that you can just kind of identify, okay, what is it that my students are going to be kind of manipulating or negotiating over the next 3 days. I will say for myself, this 45-minute class period, what takes 45 minutes in my class might take 5 in yours, or it might take 180 in yours. So I have no idea, but that's just kind of a good estimate as to what this looks like. But I think 45 or 3 class periods is what we're trying to target. As you scroll down, and also a big shout out to Eclipse and kind of their work on this and kind of streamlining. Every lesson kind of looks the same with the same lesson objectives and then the materials. Notice for a teacher, I can just look. I have the slide deck and I have whatever is forward facing to me as to the students, and then also what's forward facing just to me as the teacher in terms of what I need to negotiate. For this specific lab, all the materials I need are mostly clay and then some graphic organizers to support this. And then once you go in, then you can jump into day 1. Every lesson is broken down into an opening, body, and conclusion. And then there's background resources tied for each lesson, as well as the slides and when these activities will go. and take place. Do notice that there's not specific times frames for the opening, body, or conclusion, but it's just to navigate and understand that this all should take place within a class, could possibly take place in a class period, and is always open to you to kind of adjust to best meet the needs of your students. This is what day 2 will look like. And then if you scroll down, day 3, and then one thing I did want to call out is that every lesson has an extended lesson opportunity. One of them is the same, it's just looking at chemical engineering jobs and how do we tie this specific, what does this actually look like for a student if they want to investigate, whether it be batteries and storage or catalysts or looking at tribology or tribological effects, right? What does this look like? Where can I enter this specific field? And there's also a list of perhaps people they can contact and see, oh, who can I talk to about this? Who could I reach out to in my specific field as well? And lastly, each one also comes with a specific extension activity that is native to that specific topic. So without further ado, I'm just going to kind of jump in to what this kind of this lesson looks like. This one was we got to give a lot of love and shout out to Dr. Mariel Coker. She helped us out with this one a lot. So we're just going to jump right into the lesson plan. Students are going to be looking at this phenomenon of plastics, and they're going to dive specifically into microplastics. So perhaps your students might be familiar with the Great Pacific Garbage Patch. So if I were a teacher, I'd come in, I see, okay, I got to go to slide 3. So if I click here, it'll take me directly to the slides. And if I go from slide 3, just as what Mariana demonstrated, you can kind of just jump right in and you just follow the lesson plan to match the slides. So in this specific scenario, we're going to talk about where ocean plastics go. Students might be thinking about, they know plastics have a specific cause harm to the environment, but really what does the life cycle of plastic look like, right? So many students, they might not know that in many cases, at least in terms of human time, it might be forever, right? In terms of plastics. And what does that actually mean for the environment? Just like Mariana, we run Mariana's lesson, we want to break down what does micro to nano, what does the scale look like? And the specific phenomenon that they're going to negotiate, once we jump to it, is, well, what are the difference in these small plastics that we can or cannot see? How can they actually affect the human body? So in this one, we're going to first negotiate, well, what is the environmental impacts? And so as you can see here, as you drive down, we could talk about the greenhouse gas emissions that exist on Earth, but then also how does this tie back to how plastics are made and what is the life cycle of a plastic? Any questions so far based off of what we're talking about here? Thank you very much. So as we can see from the data literacy, obtaining and evaluating information is a big part of this first day of just really trying to lay the groundwork for why this matters. What does microplastics look like, and what does it look like in terms of how its connection back to carbon emissions, right? So day 2, we're going to look at the specific phenomenon. Day 2, all of this ties back specifically to this concept of what can we do to capture these plastics and what can we do to degrade them to a point where in this specific scenario we're looking at is into biofuels. So the reading, which this is based on, is from a Northwestern article, which students will negotiate as well. But the main science that we are, or the phenomenon that we're trying to get at right here, is that to bypass issues of inability to degrade these plastics into more, for lack of a better term, like consumable polymers, this laboratory harnesses yttrium, which is 39 on the periodic table. I got a periodic table behind me. I had to double check just to make sure. I was like, shoot, what is that again? And they basically heated this sample to melting temperatures and applied a catalyst without a solvent, and the plastic fell apart, reverting its original building blocks without leaving byproducts behind. So that's the main phenomenon is, okay, could this yttrium possibly, and you present this to students with, can this possibly be used as a way to break down plastics? What does this look like in terms of what's forward facing the students? They're going to go here. They're going to read this article just as just the one that we had just gone over. What's cool is that like if students were to see this, like I can't read this, where do I go? You can for me, one thing I might do is I might add a hyperlink to this so that if you're going to make this actually facing to students, you can just click on the link and go from there. But if you go back to the lesson plan for day 2, you can find it right here in the article for materials for the unit. Or if you go to day 2, right here, you can find the article in terms of the body of the lesson as well. So just different ways, depending on how the teacher wants to, or how you want to access the content as well. What's kind of interesting is that students will take on the role of a science, of a chemical engineer and really use science and engineering to solve this specific problem. And what they're going to do is they're going to have a challenge in which they're going to consider the phenomenon of surface area to volume and how can they design a web that can capture the most amount of these nanoplastics and break them down. So their challenge is they are going to use a web of simple geometric shapes with the goal of maximizing the amount of surface area of yttrium exposed to water. And what they're going to use to do this is actually clay. So students will negotiate different designs, right? Is this a viable design in terms of if we were to pass water through that contained microplastics, would this be a plausible design to capture these microplastics? And students will negotiate surface area. For myself, this is a great segue into cells and why cells have to be a certain size in my life science class. But this might also be for an engineering class, right? Or even a math class. I can think of like in California, this is, I think, math 2 for us, like integrated math 2, right? Like the idea of surface area to volumes and different shapes and really putting that in a real world example, right? So students can, this is a teacher walkthrough of looking at different surface areas and calculating it, like which one can actually capture more of this, which of these, if we were to coat this with yttrium, could catch more of those nanoplastics. And if you go through here, you can do the calculations. So a little bit of like gradual release of like, we can walk through these calculations. And then ultimately, while you're looking at maybe it's a crossbar, maybe it's just a single bar, right? Students are being exposed to different simple shapes as well. Are there, I saw something in the chat. Were there any specific questions so far? Oh,
No,
no.
I just
Okay.
wanted to add, Merrick, that I was going to use this for credit recovery algebra for high school this
Oh,
summer. So
that's, I think that'd be a perfect space to use it. Right. So what we're gonna have students negotiate is also the concept of like a cross section. So if we were to have like a pipe of some sorts and this water is flowing through, and you were to have a cross section of a web that can capture this, what would this look like? Students were going to learn about the different shapes and actually get a chance to design their own web. Right. So students will be given different the same amount of clay, a ruler, paper, and pencil for calculating surface area. And their job is to basically model out what a web will look like within a specific graphic organizer. So students can actually use this diagram right here if you click, and they can basically use this as a placemat to kind of build out what a 3-inch diameter pipe would look like and then kind of place their little pieces here and there. And the idea is that students, given the same amount of material, can they basically maximize surface area? And this is like for me as a teacher, again, I'm like, nanoscience is like this. Like to me, like when I heard nanoscience the first time, I was thinking like Iron Man. Like that's really where I was at, like nanotech and stuff like that, or like Spider-Man suit. So like for some, like how do I like visualize this, especially for our students who want to manipulate things? So like this is a tangible way of accessing the content and make and like kind of sense making the whole thing without having to buy like thousands of dollars of equipment or go on these crazy field trips, but just to visualize what's going on. This is such a great way to kind of enter and access this. Opportunities for gallery walks and a classroom discussion. And then once you get to day 3, this is an opportunity for them to basically refine their approach, right? So it's very similar to day 2. So if I were to go back, and I know I'm jumping through screens a lot, so thank you for bearing with me through this. But students are going to then redesign their webs and with the goal of maximizing their surface area to mass ratio. How can I get the most bang for my buck with the materials? Because although yttrium is relatively inexpensive, the I believe the lanthanides and the rare earth metals that kind of go with it in order for this to happen, they are very expensive. So students can negotiate that concept as well in terms of these materials are not limitless. What do we do to best make our design most effective? And again, there are additional materials to have students read talking about green hydrogen or the power of catalysts. This is just one avenue, but there are many different avenues that students can explore with catalysts. And this might get them thinking when they hear the term catalyst in their chemistry class, or perhaps even in their physics class, like, oh, this is not just like a chemistry thing. This is not just a life science thing, a physics thing. This can be applied in all different aspects and how there's intersections between math and science. And I'm not just learning about shapes in math. No, this could be used in my science class as well. And again, everything is listed here. These were the extension activities I talked about. And then if you wanted to dive a little bit deeper into learning about other nanocatalysts or addressing sustainable goals from the UN, you can have different jumping off points that you can go as well. That's all that I really had on my end. Is there any specific questions on what implementation might look like, or what this might look like in your class? I'm curious if you want to throw it in the chat. As a teacher, I'm always looking to kind of do better and try different things. Based off of what y'all seen today, is there something that you would do to kind of edit or change this, or and I don't know if I'm allowed to ask this or not, but like,
Yes, of course.
okay? Is this something that's like viable in your classroom? Like, you can see, like, I can see this like potentially working with some minor changes. I know I asked a lot of questions. So I'm gonna throw that in the chat real quick.
Well, people get creative with your answers. I first wanted to thank you again, Merrick and Mariana, for presenting and giving us a lot to think about. This is such a cool project, and I'm very excited to see how well those lesson plans came out. While people come up with responses to your question, Merrick, I do have a question for both of you. What was the most like surprising or exciting thing for your students when you introduced this in the classroom?
You want to go first?
Want me to go, Merrick? Okay.
Yeah, go ahead. By all
Well,
means.
I was just thinking, in day 2, there is a lab where they have to um, fill out a rectangle with graphite on a pencil, and they like hit a penny over or a small, I think, give them a small wooden cube, and then another same rectangle with nothing. And it was a great introduction to graphene because it's carbon. And they were like, and the video in the lesson talks about how graphene is a super lubricant, can be used on surfaces. And I think they were just like, Miss O'Brien, this is like the video. And I'm like, yeah, is seeing them make the connection and having a pencil that has this substance was really helpful. And I told them, well, what could you do if your key like doesn't turn in your lock? And they figured out, just rub it with your pencil because it's a lubricant. And I was like, yeah, that's what you could do.
That's
So
so
it was,
smart.
I know, I was like, what the? It really surprised me. But that, I think, seeing that the science is really practical and useful.
Yeah, I'm with my students, we actually did also like a battery lab in which we looked at like students how to design or build a battery, and they could use either like pelletized graphite or they can crush it, they can do what they want. And they were able to see like a voltage difference when they built that from one side to the other. And they were just like, and it was really interesting to hear the students because they're like, oh, like when they crushed it, they saw a bigger difference. And they were thinking like, and they actually said out loud, which I was like kind of surprised. They were like, oh, so does this mean like if we made it even smaller, we can like do like this might be even a better battery? And it was like just kind of them making that connection. It's like, okay, like I can't really demo like Mariana does a great job in her lesson of like trying to visualize what nano is and like what's how small this is, but like for them just to make that conceptual grasp that like if we were to do this, this is what could happen. Um, yeah, and then also with Mariana's lesson, I tried in class, we're one of the lessons was like how can we reduce like friction and wear, and basically one of my students decided, or my student groups, they decided we're gonna build a certain a plane that can land without like tires, and then their specific example was Taylor Swift and how she flies around the country in her private jet for different concerts. So there's like we're gonna build a special plane for Taylor Swift that won't cause wear and tear and like cause more microplastics and more emissions into the atmosphere. It was like I don't know how scientifically that's going to work, but I like the way you're thinking that you're trying to take some of these ideas and like kind of push it forward so you can see somewhat of a connection with the content. So just letting students be creative and just really letting them like giving them grace, and also yourself, myself as a teacher, grace, and like this sense making process. We're all trying to make sense of this. Like nanoscience is like y'all got there's some heavy hitters in science that like I just like I can't like get to sometimes in terms of the content, but just kind of building these lessons and negotiating them at a much more digestible manner, I think is super helpful, not for just for me as a teacher, but for the students as well.
Very well
There's a
said.
question in the chat
Hmm.
about like there's actually a couple of them from Brandon. Um, like what scared us about the topic or challenged you? Well, just like Merrick said, like the science is very challenging. And so not being afraid to ask questions and like being a student, being a student, the best student that you could be to help your students understand it. That's what I think. Okay, I need to see it. I need you to help me explain it. Um, and when you ask experts, they can explain it to you. So don't be afraid to ask questions. And I never pretend to be the expert nanoscientist because I'm not. I always say, well, what do you think? Where can we look? So my skill is helping them think about an idea and visualize it. And the actual content, I find it from the professionals. I don't know if that gets to you. The one that I think might be especially hard to teach. Um, okay, can you come back to me, Eric? Do you have something? I'm trying to think, like, well, which one?
I don't I think what I like about these lessons is that it's very approachable, and that like these are relatively simple models that we're using with students, and like we all know that models typically break down at some point, but it's just for myself, my use was specifically just to kind of introduce students to the concept and what and let them like if it's something that they're interested in, they want to dive deeper into, then by all means they can go. um, for an example, I want to call I know Dr. Elaine Reed is on the call right now, and so for one of our projects, is she's with the UCLA nanoscience team. And um, I just encourage my students, hey, submit something for a nanovation project. So this is where students can basically pitch like a Shark Tank style to of a business product that they can use that's connected to nanoscience. And I let them students pick, like based off what we learned, you can choose whatever topic you want. And then I had all my students kind of submit their potential business proposal. And then one of the teams, they're working on trying to reduce fires in the or reduce the effect of fires. We live in Southern California with the Palisades and the Eaton fires. And basically like develop walls that can have better thermal insulation, and how they're going to use
Awesome.
aerogels and and basically they want to spray on aerogels to existing like wool and different carbon fibers within walls to kind of make them more better thermal insulators. And it's like, and so literally like 2 days yesterday at lunch, I bought a blowtorch and we got some wood, and then we put some stuff to mimic aerogels, and we are just burning it, and we had a thermometer on the other side to see what would change, and just kind of like it was so rudimentary. It was like this model like makes no sense, but like they were so excited. We get to burn something, and they were all lit, and just like getting them excited. And right. So I'm gonna be the first to say, like, in terms of the complex stuff, like, I can't really speak to that, but I can speak to like making this approachable to students and trying to make it fun. So I didn't really answer your question. Sorry about that.
You're fire. There's another question in the chat. Really great resources for educators. Has your enthusiasm piqued the interest in others? How can this be expanded in all schools?
Um, well, I think Merrick and I have been doing working with the UCLA Nanosystems Institute for, I want to say like 10 years. And it does require some time, but like students, teachers are intimidated. They already have a lot on their place, and then to ask them to learn something new can be a big ask. So we're hoping that these resources are really user friendly and give teachers confidence to try new things. That's one. Try it. Just try it. You can do it, and hopefully will it'll help them because like, oh, I don't have a huge budget to buy nanomaterial. Like, what are they? So hopefully this will get them thinking that you don't have to have nanomaterials to teach nanoscience because it's the concepts that make it powerful, especially for middle school, because they're not going to be making a deuterium catalyst in my class, but they can understand the importance of surface area to volume ratio. I know if that helps you.
Is there any other questions? Take advantage. This is a discussion. Don't be shy.
I just want to say one more thing. On the slides, we hid a bunch of slides, like you can skip slide for teachers to not share with students. And those are there for you to look at, to use or not use, or do whatever you like. But there's a bunch of stuff that's hidden that is available for you to try. Because maybe if even it's just like 5 slides that you use, it could be the start um, to you trying more things.
Well said. And just because I saw the different interest in the chat, I know someone was interested in nanomedicine. These lessons plans are more in climate change, earth, environment. But there's a lot of resources that my office can help point you to if you're interested in nanomedicine. We've had a session in the past about agriculture and nanotechnology. So any other topic that maybe your students or the population that you're trying to reach is interested in, please reach out or let us know right now, and we're happy to connect you to the experts in that area or resources that already exist so you don't have to reinvent the wheel. And with that, um, any other last minute questions? Yes. We Uh, for me, tr as being in the federal government, we don't really have the connections to the administrators to reach out for this with these resources. It has been really one-offs that we get to meet someone and like or work with a teacher and the teacher goes to their supervisors. But if there's a way or there's a if you're interested to have that in your school district and there's a way for us to talk to someone, please reach out. We're happy to talk to whoever and help spread the word about these resources. Okay, well, thank you again. Virtual round of applause to Merrick and Mariana again. And oh, thank you. But I'll reach out to you afterwards. And is there any specific thing that you would be interested in, Jared?
Good question. So, I work at a service agency, in ESA, and we're developing a K through 12 nanotech, AI, and synthetic biology lab. Um, and so I do have some I just need to talk to probably you and some others a little bit more. This is the first forum I've attended, but the way we are setting this up, we serve the local districts in our county, 28
Mhm.
local districts. So this service that we will be setting up, teachers and kids will come out for approximately about a week, and we're going to be doing different activities in this lab that we're building. So I guess I'm open to any and all things, but we're not a traditional school district in that standpoint. I mean, we are a public school. We're just a service agency, but we're looking at doing some things at a very large scale. So I'd love to talk maybe some more. I don't want to take up everybody's time.
Wonderful. Yeah. I have your email because you registered, so I'll reach out with more information. We can set up some time to talk. And thank you for coming for the to the Nano Educators Forum. I hope to see you in the next one and all of you as well. I'll reach out to you. And for everyone else, thank you again for being here. We meet 4 times a year. This is the last session of the school year. Our next session will be in September. I'm hopeful that we can highlight the other two lesson plans developed through this program, either in the September session or the November session. But we will be reaching out with more information as the time approaches. For everyone that registered today, you'll get a summary of the session, the video, and all the resources that were shared in a nice little package. And with that, good afternoon, and hope you have a good day. Bye bye.